Experiment on dynamics, electricity and optics. The Newton software offers a completely new way to learn and teach physics, enabling the exploration of simple machines, mechanisms,
kinematics,
dynamics, thermodynamics, electricity, and optics in 3D on a computer.
Students can interactively build, manipulate, and investigate realistic 3D physics experiments, solve problems, and much more. Newton operates under simulated laws of physics, enabling you to interactively build, manipulate, and investigate your experiments without the constraints of physical models. At the top of the application window, you'll find several toolbars. The object bar is one of the most important. When creating an experiment in Newton, you can choose from a wide selection of real-world and abstract objects, ranging from simple geometric shapes, like bricks and spheres, to complex instruments, such as stands, slopes, and cars, as well as constraints, including various types of joints and springs. More than 350 example files and problem files are available on a variety of topics. Now, we'll guide you step by step on how to use the program and create compelling experiments and demonstrations. To create a new experiment, click the New icon. This will open empty 3D and description windows, and the screen will display only a tabletop. When the description window is in edit mode, the vertical description toolbar should be visible, offering icons to assist you in creating the window's content. Let's begin building our first simple experiment. You can find the ball object on the Objects Toolbar's Bodies page. Click its icon, and the ball will immediately appear in the 3D area. You can move the object within the XY plane while keeping its Z coordinate unchanged. To position the object correctly along the Z-axis, click and hold the Move Up-Down icon and use the mouse. To start the simulation, click the Run button and observe the ball on the screen. Now let's create diagrams to represent the motion of the ball. Locate the diagram icon and click it to open the Diagram Properties window. You can then create a curve and place it in a diagram within the description window. In the Diagram Properties window, select the Position Z node and place the diagram. Let's run the simulation to observe the falling ball's motion along the Z-axis over time. Let's construct a coupled pendulum. Place a stand from the Objects toolbar onto the scene. To position the stand and ball precisely, use the 2D view mode. To attach the hinge to the stand, select the stand, then click the Hinge button. Link the hinge to the ball. Now you have a simple pendulum. We'll duplicate the pendulum using copy and paste. Position the two pendulums next to each other. We connect the spring to the balls. The connectors at each end of the spring are drawn to the balls, automatically attaching themselves. Double-click on the spring to open its Properties window. Set the stiffness to 1 Newton per meter. Plot the x-coordinates of the two balls over time. Swing the pendulum and observe their motion. In the diagram, The red line represents the motion of the left pendulum, and the green line represents the motion of the right pendulum.
Observe that, when one pendulum is set in motion, its mechanical energy is transferred to the other through the coupling, and this transfer oscillates continuously between the pendulums. This demonstrates the law of energy conservation. If we ignore friction, the total mechanical energy of the system remains constant as it is exchanged between the pendulums.
In the next topic, I'll show you, through an example, how to add an expression to a diagram. Open the exampled pendulum with large angle from the Dynamics library. In this example, we demonstrate the motion of a pendulum. The software-generated motion is represented by the black dots on the diagram. Pendulum motion can be described using several mathematical approaches. The simplest approach, suitable for high school level, is to model it as a harmonic oscillator, which provides accurate results for small deviations. This is shown by the red line. A more accurate approximation, typically covered at the university level, is represented by the green line. The exact solution, requiring higher-level mathematics, is shown by the black line. The formula for each calculated motion can be displayed on the diagram. The calculations are displayed on the pages of the description window. Here is the exact calculation, using Jacobi elliptic functions and elliptic integrals, which you can also find in the Newton software. Here, you can enter mathematical formulas. You can write the expression across multiple lines if that is more convenient. In the next topic, I will show you how to easily create a circuit. Place a switch, a battery, and a lamp onto the scene from the Electricity Objects toolbar. Connect these parts with wires. To connect the parts, move the cursor over an appropriate pin node until a small drawing pen icon appears. When this icon appears, click the left mouse button, draw the wire, and click the left mouse button again at its endpoint. To test its operation, move the cursor over the switch and toggle it by clicking the button. The switch can be toggled, for example, by dropping a ball onto it. Another interesting area of physics is optics. With Newton, you can set up various optical systems and visualize them realistically using Newton's ray tracing engine. The optical elements are located under the Optics tab on the Objects toolbar. The available components include various lenses, mirrors, prisms, a ray emitter, and a canvas. Open the converging lens example from the Optics library. In this example, we will demonstrate a simple optical system using a convex lens and a canvas. To view the optical demonstration, click the ray trace icon.
If we change the distance from lens to the target, or the distance from lens to the canvas, the projected image is continuously redrawn. This concludes our demonstration of dynamics, electricity, and optics experiments using the Newton software. For more information, please visit our website at www.newtonlab.com.